evening, everyone. Today we're diving into one of the most fascinating areas of chemistry, the synthesis of new elements. Scientists around the world are creating new elements that don't naturally exist on Earth, pushing the limits of the periodic table. But how do they do it? And why does it matter? Well, joining us today is Derek Huff.
Thank you for having me.
Well, let's start it simple. Tell us about the nuclear chemistry.
Well, it revolves around four key concepts: fusion, fission, radioactivity, and an unstable nuclei. So an atom is stable when it has an ideal ratio of neutrons to protons in the nucleus. And as we all know, the nucleus consists of neutrons and protons. In small atoms, this ratio is about 1:1, but in larger, denser atoms like lead, proton repulsion actually adds up, and it requires a lot more neutrons to act as a buffer. This shifts the stable ratio to about 1.5 to 1, where neutrons are 1.5. An atom becomes unstable when these ratios are off, and this leaves the nucleus with excess nucleons, which are either protons or neutrons.
Okay, so when an atom has too many neutrons or protons, it needs to get rid of them?
Exactly. This is called radioactive decay, and there are 5 main types of this shedding. The first is alpha decay, which occurs when an atom has too many protons packed together. It's usually has an atomic number greater than 82. The nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons, identical to a helium nucleus. This decreases both the size and the atomic number of the atom and makes the atom more stable. Well, beta decay happens whenever an atom has too many neutrons. It converts a neutron into a proton, and this balances the charge by creating a high-speed electron, or a beta particle, and shoots this out. This moves the atom to a more stable ratio. Similarly, during positron emission, an atom has too many protons and converts a proton into a neutron. To balance the charge, it emits an electron, neutrino, and a positron, which is a positively charged electron. Electron capture also targets an excess of protons, but it occurs only if the nucleus lacks the energy to convert a proton directly. It sucks in an electron from its own inner electron shell to turn a proton into a neutron.
Okay. Wait, where do gamma rays come into mix?
Right, so gamma radiation occurs after alpha or beta decay. The remaining nucleons are left in an excited state with tons of energy, and as they shift, they drop. As they shift and drop to lower, calmer energy levels, they release that energy as gamma rays, which are just pulses of electromagnetic energy. Because gamma rays are photons and not actual matter, the atom loses no mass or particles during this process.
Okay, that makes sense. Wait, so what was that other thing you were talking about?
Right, yeah. So fusion and fission, both are processes that are undergone by scientists to create energy or new elements. Fission is just the process of breaking atoms, and this is done by sending a fast-moving neutron into a heavy atom. This collision releases other neutrons, which do the same to other atoms, creating a self-sustaining chain reaction of breaking atoms. This is the main technology used in nuclear power plants and bombs. Fusion is the process of combining 2 light nuclei into one larger nucleus. This process requires tons of heat and pressure and is very expensive to recreate in a lab. 2 nuclei are heated and then put under extreme pressure. Because of the similar charges, neither one are really inclined to combine. But under this heat, they vibrate so fast that they collide in a way that pushes past these charges and allows the nuclear force that attracts particles in a nucleus together to kick in and combine the elements, even if it's only for a few seconds. This is also the same process that powers our sun.
Wow, that sounds complicated. I could never figure that out.
Yeah, and for years, no one else could either. A few scientists come to mind when we think of nuclear chemistry that we can attribute it starts to, like Marie Curie, who was the first one of the scientists to work in the nuclear field. She and her husband discovered both radium and polonium. The discovery of these led to the discovery of radiation and radioactivity, and she discovered that radioactivity was a property of all atoms, and it laid the foundations of nuclear chemistry. She went on to win 2 Nobel Peace Prizes. Ernest Rutherford discovered the nucleus and alpha and beta particles. He formulated the laws of radioactive decay and that atoms would spontaneously transmute into other atoms. Frederick Soddy worked with Rutherford. He scientifically developed the idea of isotopes, which were atoms of the same element with varying weights due to more or less neutrons. Lisa Meitner and Otto Hahn credited as scientists who bombarded uranium nuclei with neutrons in the effort to create atomic fission. Using this data in experiments, they discovered that uranium nuclei were splitting in half and they coined the term atomic fission. James Chadwick was also the first scientist to discover the neutron, which led to many other discoveries.
Oh, that's crazy. Well, now that I have a grasp for nuclear chemistry, let's get down to business. What is this, nuclear synthesis of new elements?
Right, so let's get down to business. We're attempting to fill in the periodic table and create elements that are not typically found in nature, like element 120. Because these are not naturally found, we use nucleosynthesis, which is the process of forcibly jamming high-speed isotopes into certain elements using a particle accelerator to break apart the forces that hold the nucleus together. After these are broken apart, they combine with each other to produce nuclei that hold a predicted amount of protons like 117 or 120. After uranium, the repulsion of these protons kind of starts to outweigh the strong nuclear force that holds the neutrons together, so elements after uranium are extremely unstable, which makes this task very difficult. To put it simply, nuclear synthesis is just the process of creating entirely new elements by forcing atomic nuclei together in laboratories. Scientists smash atoms into one another at extremely high speeds, and occasionally those nuclei fuse together and form brand new elements. Again, if only for a couple of seconds.
So scientists are making matter that never naturally existed on Earth.
Exactly. Most of these are called super heavy elements, which means they have more than 104 protons.
Continue diving into this chemistry. What exactly does nucleosynthesis mean?
Well, nucleosynthesis is the overall process of creating new atomic nuclei and new elements.
Okay, so nucleosynthesis is like the big picture.
Exactly. It's the overall process of forming new nuclei and expanding the periodic table.
Okay, so where does nuclear fission fit into all this?
Well, nuclear fusion is the specific reaction that scientists use during nucleosynthesis. Fusion occurs when two smaller atoms combine to form one larger nucleus, like we stated before.
So fission is the actual chemical process occurring.
Exactly. In laboratories, scientists use fusion reactions to force atoms together and create heavier elements.
So in this topic, fusion is the method that scientists use to achieve nucleosynthesis. But how does a scientist actually create one of these elements?
So, scientists use machines called particle accelerators. They fire one atomic nucleus into another, and if the nuclei overcome their electrical repulsion, then they fuse together and form a heavier nucleus.
That sounds extremely difficult.
Oh, it is. Sometimes scientists work for weeks just to create a few atoms that exist for less than a second. Their half-lives, or the time that it takes for half of the specimen to radioactively decay, can be mere moments due to the unnatural nature of these elements and their extreme repulsion from one another.
These elements disappear so quickly. Why do we create them?
Because they help us understand how matter works at its most extreme limits. Scientists are searching for something called the island of stability, where super heavy elements may survive much longer than current ones. According to Lawrence Berkeley Lab, once you get past uranium, elements are not stable. However, there's this belief that if you get heavy enough, there's an island of stability.
And if the scientists find this island?
Well, it could lead us to an entirely new discovery in chemistry, physics, medicine, energy research. We could perform experiments on completely new types of matter and understand what makes up our world to the highest degree possible. The technology that created new elements can be implemented to PET scans, proton beam, cancer therapies, security imaging. It would push scientists to move the boundary of what we thought was possible in nuclear chemistry entirely.
Okay. Before scientists started creating these elements in laboratories, where did the elements originally come from?
Believe it or not, the story starts with the Big Bang.
Wait, so you're telling me like the beginning of the universe is where it started?
Exactly. Right after the Big Bang, the universe was incredibly hot and dense. During the first few minutes, the earliest form of nucleosynthesis started, the natural form. Scientists called this the Big Bang nucleosynthesis. I mean, that makes sense, right?
What elements were created back then?
Well, it was mostly hydrogen and helium, tiny amounts of lithium. At that point, the universe still didn't contain heavier elements like gold, uranium, or iron.
Where did they come from?
Well, from stars. Inside stars, nuclear fusion constantly combines smaller nuclei into larger ones, like we had described earlier. That fusion process powers stars like our sun. Over millions of years, stars create heavier and heavier elements through stellar nucleosynthesis.
Okay, how did humans go from observing the stars to like creating our own elements?
Well, in the 1900s, scientists began experimenting with radioactive materials and nuclear reactions. Researchers like Ernest Rutherford, Enrico Fermi, and Glenn Seaborg helped develop modern nuclear chemistry.
And eventually, scientists started creating artificial elements?
You got it right. Using particle accelerators and nuclear reactors, scientists learned how to force nuclei together artificially.
So that the laboratories they're using is basically just trying to imitate what happens inside the stars.
In a way, yes, we recreate tiny versions of those extreme nuclear conditions here on Earth.
Okay, let's move on to our next segment. When people hear nuclear chemistry, they immediately think of danger. Are there any risks involved in this?
Yeah, so after the element uranium, all super heavy elements emit large amounts of radiation and have really extremely short half-lives. So whatever new element scientists discover in the lab will be extremely dangerous and uncontrollable. Nuclear fusion can create fissile materials such as plutonium-239, which is a material that's used in nuclear bombs, and the more we know about this topic, the easier it is for the government to make these nuclear bombs. It's extremely expensive, costs multi-millions of dollars to perform experiments that use up valuable stocks of isotopes, and power particle accelerators have to be running 24/7 for months at a time, using tons of energy in the process. However, these experiments happen under strict regulations and safety precautions and procedures.
So while there are risks, there are also major scientific benefits.
Oh, absolutely. Nuclear chemistry isn't just weapons and disasters, it's also discovery and understanding of the universe. Nuclear chemistry, and more specifically nucleosynthesis, gives us many opportunities in the development of science. We could remap our understanding of the atomic nuclei, prove where the periodic table would naturally end. It would theoretically allow us to replicate the environments that formed our universe and the elements.
Okay. I think we can move on. What does the future look like for this field?
Right, so scientists are currently trying to create element 120, which would begin a completely new role in the periodic table. Recent experiments showing promising new methods for creating heavier elements in the commercial space. Startup in Virginia is developing the first commercial fusion reactor, the first one of its kind, in a multi-million-dollar facility called ARC. This facility will be able to produce 400 megawatts of energy, enough to power 150,000 homes. And as we further develop this topic, we gain the ability to make vast amounts of clean energy that is sustainable for the future. And that is increasing rapidly.
So the periodic table might not be finished after all.
Not at all. Science is definitely still exploring its limits, and will be for a while.
Well, Dr. Huff, thank you for joining us today. If you had to stay, what is your stance on the use of nucleosynthesis to make a new element?
Well, of course, I believe that while God's natural world should be well left alone, there's no denying the tremendous strides that we have made and will continue to make in the study of nucleosynthesis. While yes, the cost of the process and overall energy consumption is more than we would like, the benefits of cancer treatment, understanding the world around us, and discovery of just how this universe came to be vastly outweigh the negatives. And not just for nucleosynthesis, but for nuclear chemistry as a whole.
Agreed. Thank you so much for your time.
Right? Thank you for having me.
You heard it here first, folks. The synthesis of new elements shows that nuclear chemistry is far more than explosions and radiation. It's about curiosity, innovation, and expanding the human knowledge. Reporting live, I'm Alec Marino. Thank you for listening. Wait! Before you go, we have a brand new solo put on by our scientist, Derek Huff. It's titled Nukem. This song is already on set to be a double platinum and win multiple Grammys. Have a listen.
Yeah, I'm on top of being a nuclear synthesis scientist. I also lay down mad bars. Check it out.
Yo, it's your boy D Huff. Make this rap 'cause I'm a chemistry buff. Nucleosynthesis, it ain't that hard. Your boy D Huff will tell you where to start. First, all you need is a particle accelerator. Going fast with atoms like it's Eve on an elevator. Nuclei split, like fire, going to see you later. Don't get excited 'cause the atoms gonna fuse together. D Huff pushes down at a incredibly fast speed. If you need help with you can come and ask me. Half-life, baby, yeah, really into hard to see. Still see decay over half their life simply. New elements gonna decay super fast. Matter of seconds, we got Nick Queen from the tracks fast like a train. Think you can catch that? Scientists did, just a matter of the fact. D Huff, big stuff, real tough, chem buff, all off, no puff, real rough, double stuff. You like chem stuff, it ain't that tough. Now I've got something you kids will love. Fusion, now you don't frown. One breaks the nucleus, the other builds them down. Wants the same pressure, gotta give the thing a pound. Call me nuclear fission 'cause I'm about to break it down. Nucleus goes boom, forces attract. New nucleus forms, only for a sec. New element, new cool tech, new kind of studies, nucleo facts. Let me wrap it up while I'm breaking it down. I'll be on my way, but don't you frown. You'll never find a rap that goes as hard as this. It's 7-6, cuz it's nucleosynthesis.
All right, roll the credits.